Welcome to day 2 of LevelUp X07. Now, if you have just randomly mashed your keyboard with your face and somehow landed on this page and you have no idea what LevelUp 7 is, it's a conference about hacking. And when I say hacking, I'm not talking about like the general hacking term that gets overused today, like productivity hacks and mindfulness hacks. No. I'm talking about actual computer hacking, like Die Hard 4 and Mr. Robot, right? That's what I'm talking about.
But yeah, I think maybe we'll just start introing Buses. Buses, a skilled hacker, and is definitely not afraid to dive deep into any kind of technology and different protocols and things like that. Basically, he's been a lifelong tinkerer and a self-taught hardware hacker, which is pretty amazing. Has a bit of experience with automotive radio frequency hacking and IoT hacking, and is always looking for new things to break, which is, in my opinion, pretty awesome.
Hello. Thanks everyone for tuning in to my talk today. Hardware Hacking for the Masses and You, version 2. I gave a version of this talk 2 level ups ago at the 5th level up, and I thought since then I've learned a lot myself, and there's a lot of things I think I've improved on, and I would really love to make another version of this kind of intro to hardware hacking content. So let's jump into it. I am BusesCanFly on Twitter. I love doing hardware and automotive security research. My experience with BugCrowd is I've done some general bug bounty things, but also a handful of hardware and automotive bug bashes with BugCrowd. I'm a student, and yeah, huge shout out to Teams Dumpster Fire and ADD Vulcan. Yeah, I guess the normal disclaimers. I'm not a lawyer. This is not a perfect presentation. Be responsible, hack stuff you own. Don't be dumb. Yeah, I'm not a lawyer. Overall, this presentation, I was hoping to give kind of like a more general overview with hardware hacking things. This is by no means a field guide or the perfect Bible of hardware hacking. My intent is really to help people kind of demystify hardware hacking for a lot of people. I know for myself, getting started in a new subject area can be really difficult, but as soon as I just get to and start with learning something, it usually gets a lot easier and I have a lot of momentum. But I specifically benefit a lot from when people shove me through the basics, and this is kind of my intention to show how I think there's this big stigma around hardware hacking being really difficult and really crazy, but like a lot of smart, incredible software people in software based and web security researchers will say like, oh, hardware seems really difficult and all that kind of stuff. But I think it's not any more difficult, but it's just a little more esoteric, and maybe not as many people are experienced in it. So I hope I can provide at least a little bit of information to kickstart your learning in that, because it is a wonderful subject and I love it very dearly. With that being said, this presentation is not everything you need to know. For example, I'm not going to teach you how to solder or what a resistor and capacitor are. There's a ton of already made amazing guides online for that, and I don't feel that I need to make a worse version of those. This is also, I'm not dropping any cool 0 days or anything. This is just kind of a general basics overview. And one thing I'm not going to talk about is common web vulns. That's a great thing with hardware devices, getting command injection through web interfaces and all that kind of stuff. That's wonderful stuff. Also a ton of good blog posts and resources about that, but not in the scope of this talk. So, yep, some frequently asked questions. Hardware hacking, just like if you ask what is web hacking, it's a really general thing, but as with anything with hacks, we're trying to make something do something it's not supposed to or it doesn't want to. A question I get a lot about hardware hacking is the money side of things, because there are people with 5-digit costs on some of their tools, and they buy all this crazy tier 3 stuff, but you can do a lot with very little money. I think first time I did anything with hardware hacking was a router I pulled out of an electronics recycling box, and a $3 serial cable I got from Amazon. And that was enough to get me a shell and a router. So you can do a lot with very little. Some tools are helpful and make life a lot easier, and I'll touch on that a little later. But you shouldn't be shying away from hardware hacking because of it feeling like an expensive start. Another very common question, is hardware more difficult than software? I don't think that's a really answerable question. They're both very broad subject areas, and they're too big to compare directly. I think anyone who is interested in hardware but shying away from it because they think it's difficult, just jump in. You're bound to find something that'll click for you and that'll work out really well. And what kind of hardware are you going to be talking about? Basically whatever you can get your hands on. In this talk specifically, any of my demos and pictures I'm going to be showing are just some old routers I had laying around. Routers are great for this because they are usually almost always a little more powerful. Like they have usually an ARM chip or maybe MIPS on a rare case or something like that, but not some sort of just microcontroller with a Wi-Fi dongle basically. And routers also usually have a decent amount of debug interfaces, and they're just kind of fun to play around with and cheap for specifically really old ones that no one uses anymore. Super cheap, secondhand or third-hand even. With hardware and software, there is that kind of middle realm firmware stuff, and that's where it's actually a great place to get your feet wet. You don't need to buy hardware or have any hardware to kind of get started with a lot of what hardware hacking is. A lot of manufacturers, when you look at their websites, they provide firmware downloads for upgrading it yourself. A lot of devices have like an automatic firmware update or a button you can just push and it calls out to the server, so it gets some firmware from an endpoint and applies it to itself. But a lot of the times, you can just download them online. And if it's not the manufacturer, someone may have published some firmware for a specific device you're interested in. Now that's true, just download the firmware and reverse it from there, just to get started. But some very quick tips, I guess strings, the command is really underrated, I think in a lot of aspects of security, but especially with hardware. You can pull potentially even like encryption keys with it if something was very poorly made. But aside from that, binwalk is just an incredible tool. It's not really a firmware or hardware tool, it's in general just file carving. Just when multiple files are in some sort of big blob, it can pick out with the magic headers where a file starts and ends. And with firmware, there's generally more than one file, or file systems, even multiple. Let's see if let me grab a pointer. Up here is the output of binwalk tac capital E on a firmware file. That is entropy analysis. There's a lot of pretty crazy math and fancy stuff, but basically, if you just see a line right about the 1.0 mark with a drop down, that's a good hint that this firmware is either compressed some ways or encrypted. That's generally what we look for with the entropy analysis, because the firmware's unencrypted, there's going to be a lot of noise, like sharp drops. It's not just going to be a straight line, and that's what we hope for, because then you can just kind of go straight into extracting and playing around with it. But if it is encrypted, there's, depending on the situation, what they're using, what kind of, basically how the firmware was made, I would recommend just looking it up. Tons of blog posts for working with encrypted firmware or pulling encryption keys and trying to decrypt it. There's just too many situations to cover in a kind of broad statement. But let's assume, like the example here, your firmware is likely unencrypted by all this kind of noise going on. Then these two flags for binwalk, E for extract and M for matroshka, which is just kind of a recursive extraction, will take a file, it'll look at all the magic headers inside there, or the magic bytes, sorry, the file headers, and carve them out, basically extract them all. In this output, you can see in this example, it's found a squashfx file system and a bunch of XZ compressed data. The file system, what we're interested in. In this case, it's going to be the root file system, but we'll get to that in a second. Some of the things you can often find are files for the bootloader. U-boot is super common on embedded and IoT devices. The U-image headers are a dead giveaway that you're going to be working with U-boot. SquashFS, JFFS, and a few other file system types are super common. And if you want to skip the binwalk route for some reason, or you're trying to repackage some stuff, Sasquatch for SquashFS and Jefferson for JFFS are both tools you can install, apt install or whatever your package manager of choice is, and you can kind of repackage those devices. And sometimes you'll see like PEM files or certain certificates for either code signing or the firmware signing. It varies, but they're not uncommon. In this example here, I have a firmware called fs.img. I extract it with binwalk here. You look in the directory, we see a squashfs root file, and we go into it, and you see the root file system. One of the things that's just a quick thing to grab is the etc shadow. I'm not going to show it here because I don't want to identify what device this is. But in this example, let's say you have the firmware. You get the shadow file by extracting the firmware, and when you get the device, there's like a SSH or telnet port open where it just prompts for a username and password, and bam, you just got it from the shadow file. Here's kind of an amazing resource for hardware hacking, two of them, but it's public information. Obviously, Googling or DuckDuckGoing things is pretty obvious, but the FCC database is a goldmine of information for hardware hacking. Any device that's sold in the US that has to transmit on any radio frequency range, so Wi-Fi, Bluetooth, like 433 megahertz, or like FM radio, anything like that, you have to register with the FCC and get your device certified. A part of that certification process is including documentation, images, the testing of your device, and then it all gets put publicly online. And in the next slide, I think I will show the process of getting this information from the FCC database. But all you need to find this kind of information for a device is the FCC ID. And I'm sure many, if not all of you, have seen these kind of stickers on devices, like even remotes sometimes. But you'll see some sticker, there'll be some logos from certification organizations and stuff like this. It certifies that this device will receive whatever information is given, and it won't transmit on whatever. Doesn't matter. This is all what we're interested in, this FCC ID. This is a picture from one of the routers I'll be using in this talk. And this ID, which I'll show in the next slide, is all you need to get internal pictures, test data, user manuals, everything like that. And the easiest way to do that, you can do it directly through the FCC website. It's just kind of a pain, as most government websites are, to navigate. So a bunch of people have made some nice websites like FCCIO or FCCID.io. There's a bunch of them. Just Google or DuckDuckGo FCC ID lookup. In these two, you just put the FCC ID after as a parameter, and it'll forward you to the FCC website where all the information is. Yeah, you commonly find all sorts of really good stuff. And I'll dive into that on the next slide. Aside from the FCC database, data sheets are super useful. A lot of times hardware hacking, all of the time with hardware hacking, when you open up a device or get access to the PCB, the circuit board with all the stuff on it, you may kind of by instinct recognize what a lot of parts are responsible for, but at the same time, a lot of it's going to be unknown. Like if you have no clue what this chip is just by looking at it, that's completely fine. A lot of the times they'll have this text on it, and it's something. If you just put it into your search engine of choice, you can usually find a data sheet, and it tells you what every pin is for. It'll give you some specifications. It'll tell you what the device is overall in the first case. So for this example, this is a SPI flash chip. So this is essentially the storage of an IoT device, and these chips are wonderful for hardware hacking. I'll get into how you can pull data from that later on. But yeah, data sheets are super useful. In some cases, with some kind of higher level chips, you can run into issues where the data sheets are like, you have to pay $10,000 something for, usually companies are supposed to buy them when they're producing something, and it's kind of annoying. They're stuck between some huge paywalls. But more often than not, you'll be able to find a data sheet for most of the chips you look at. Oh, and here's what I was talking about with the FCC database. So when you put your FCC ID of the device you're interested in into FCCIO or something like that, it'll forward you to a page like this. There'll be a little pop-up you have to click OK on, but when you see this, there's going to be multiple options most likely, and that's just because there are different frequency ranges. You can basically always just go to the first option here. If you click Detail, it'll take you to this page, and what I always go to first is the internal photos. As kind of a unrelated tip, if you ever lose your user manual for a device, the FCC database almost always has the manual. Like it just has a PDF attached here. So I know there's some sites that aggregate them and have a listing of all the user manuals, but this is another way to just get it yourself. But yeah, internal photos are great. For example, from this FCC sticker with this FCC ID, the internal photos lead to this picture. This is from the manufacturer, and while this one's not super extensive, a lot of the times you'll get close-up pictures of all the chips, or at least a lot of them, or at least every angle of the device. They have to show off most of it. This was the whole internal photos for this one. It's a bit of an older one, so it doesn't have as much information. But I highlighted right here 2 debug interfaces on the board. And I'll get into what debug interfaces are and how to identify them. But basically all you need to know is this is great to know. If you're looking to buy a device for just the purpose of hacking it to do something, or you want to do some research before you open it up to see if you even need to, you can, without putting any money into it, just do a quick search and you have all the information you need. You could also glean some more information if they were higher quality pictures and you could zoom into them, what processor they're running, what kind of flash things, and if you needed to buy flash chips, sorry, if you need to buy any adapters or something like that, you could figure that out beforehand. Oh, and as I mentioned, debug interfaces. The general idea is just the developers who make these devices, and when they're manufactured in whatever assembly lines, the code needs to be put on them somehow. The chips don't come pre-programmed from whoever makes the chips. And sorry, for anyone who doesn't know, when I refer to chip, I'm referring to these like ICs, integrated circuits on a board, ranging from flash memory, storage, to processors, to just a resistor, anything like that. Well, the resistors aren't chips, but ICs and processors, things like that generally. That's what I'm referring to. Basically, if you ever see a little black box on a circuit board, that's what I'm talking about. But yeah, they don't come pre-programmed, obviously, because they're not device-specific, most of them. So people need to put the code on somewhere. So you have debug interfaces, both for loading data, interacting with the device, or debugging it, like with GDB even. There's a lot of common formats. We'll get into that later. But the most common hardware communication protocols are UART, JTAG, I2C or I2C if you want, and SPI or SPI. In this presentation, I'm going to talk about UART and JTAG because that's kind of what's most interesting in the quick and dirty hardware hacking realm. But if you want to get into more electronics development, like playing with Arduinos or Raspberry Pis and all that kind of stuff on the hardware side, learning about I2C and SPI are great. Highly recommend watching a few YouTube videos and you'll be caught up. They're really simple. They're based in hardware, so there's not a ton of abstraction there. And we'll get into all these things later. As I mentioned briefly before, sometimes if you open up enough devices and get familiar with hardware, there's some things you can just identify just by looking at them. And I thought I'd cover some of the quick ones. So this, for example, are all pictures from a router and a Wi-Fi camera. They're mixed in, it doesn't really matter. But what I look for, at least when I open the device, the first thing is debug interfaces. You can see these things right here, these 4 pins in a row, and we'll get into the specifications of each debug interface later, but there's more examples here. Sometimes you have headers soldered in. This is a great sign. They did a lot of work for us. Some open pins, 2, 3, 10, 4, it doesn't matter. These kind of exposed pins are always a great thing to see. That means it might be at least a debug interface, and again, later in this presentation, we'll get into how to walk through finding out which each pin does, or if it is indeed a certain debug interface, UART, JTAG, anything like that. And so that's always great to look at. The second thing is some sort of storage, because you don't even have to power on the hardware sometimes to get the firmware off of it. You can just dump it off the chip itself. And kind of as I've been saying over and over again, I'll cover that later in the presentation. But something like this, where you have the little legs sticking on each side of a rectangular chip, most likely a flash chip, and that's great to see in the TSOP package. Alternatively, you can also have a flash chip in a different package, which I don't think I have on this slide. This looks like one, but isn't. We'll get into that. Oh yeah, sorry. I'm all over the place, but this is a diagram of, or a picture of the most common package types. So when you see these kind of chips, like this one has long legs sticking out, short legs, no legs apparently, they all electrically work the same. There's basically a wire or a trace in the PCB that goes to a component for communication. For spatial reasons and other like physical reasons, chips are designed differently. With a lot of through-hole things, you have dip. BGA is when there's little solder balls under the surface of the chip. That's really space efficient. You have SOP, there's like TSOP, QFN, QFP. Don't worry about memorizing anything like this, but you'll see that chips look differently, and that's okay. They're not anything different. Aside from BGA, they really all have the legs sticking out in some degree, so you can solder to them or poke at them with a multimeter. But let's move on to different components. This little block of shiny metal is an RF shield. Usually you have things, well, RF as radio frequency, things that generate RF are usually housed in these for protection, both for themselves and for other components. They can be in all sorts of shapes and sizes. Some of them are removable. You'll see little kind of clips to hold it in place, and you can just take a set of tweezers or even your fingers and pluck it off and look under. Sometimes they're soldered down. If you want, you can just cut them off or pry them out. Not super important. Also on the FCC ID, as we mentioned, when you look up the FCC ID, a lot of the images will have the RF shields removed for their registration purposes, and you'll know whether or not you need to rip the shield off or not. Another thing to look for is these kind of adapters. As labeled, they say Wi-Fi. These are the same picture, just with and without this cable. I believe they're called MCX connectors, and they're usually for antennas. Phones have these on the inside, both Android and iPhones. You will see, if you open it up, I guess not anymore because we have glass backs, but the older ones, if you open them up, you'll see this kind of wire, and they just pluck off really easily. A set of tweezers is great if you don't want to bend it, but this generally indicates that that's where the antenna connects, and you can pop those off really easily. This is as we saw in the earlier slides, a flash storage chip. We'll talk about those later. And then these big blocks, the BGA style ones where the pins are under there with usually lots of PCB traces or connections running to them, those are usually the CPU or some component like that. Okay, let's get into our first communication protocol with hardware. As I mentioned, there are these things called debug ports, debug pins, or interfaces, and really all they are just little circles of metal connected over a wire to the processor. It's great knowing that they exist, but you need to know how to interface with them. One of the most common ones is UART, or Universal Asynchronous Receiver Transmitter. It's super simple and bare bones. This is a little, excuse my terrible PowerPoint drawing skills, but just a little diagram I mocked up. One of these in this image is the host device, and one of them we can call like a client. In this case, we can pretend this is our hardware and this is our adapter. There's a thing called VCC, which is voltage, 5 volts, 3 volts, doesn't matter. Basically, for our purposes with hardware hacking, you just always want to ignore this, and I'll mention this again later on when it becomes a little more important. But for right now, let's worry about these three, which is TX, RX, and GND. GND is ground. If you know stuff about electricity and circuits, ground is kind of a shared thing. It just kind of needs to exist. Sometimes, like when you have 2 pins, they won't break out ground for you because you can just find one. Oh, here it's even labeled. But a lot of cases you'll see 3 pins for UART or 4 pins. This is 5 or 4 pins. Usually ground, RX, TX, where ground is square. But UART, TX, sorry, I forgot to mention, TX and RX stand for transmit and receive. You don't hook up as what might seem natural, transmit to transmit, because that's essentially like 2 people talking at the same time. You want to hook up the transmit to the other device's receive, and one device's transmit to the other one's received, so they can talk at the same time, or asynchronously. And if you don't want to talk to the device, you can always just not hook up your transmit connection. It depends on what you're doing. And oh yeah, sorry, baud rate is important. So whenever UART is mentioned, there's always the question of what baud rate it's talking at. Baud rate is the communication speed. Basically, how many bits per second can it send? And it's important to know because if you're listening at a certain speed and the device is talking at a different one, all you're going to get is garbled information. This is a capture from a I use a logic analyzer on a router's UART interface to kind of show what the protocol looks like visualized. This is essentially a recording of the device's transmit pin, and you can see UART usually hangs around 2.5 volts or 5 volts sometimes, and it drops low to send data, which is kind of uncommon, which is good to know. And in this case, you can see these little waves. That's the actual transmissions. By staying up at 5 volts here is a 0, and dropping down to 0 volts, or roughly 0 volts, is a binary 1. And in this case, this little section of signals makes this hex character, which decodes to an ASCII value. I don't remember off the top of my head. And the width of these is, so this would determines also part of the message. So this would be 2 1s in a row, while this is a 0, this is a 1, this is a 0, things like that. And by changing what those 0s and 1s are, that's just binary, translates to hex, in this case an ASCII character. It doesn't have to be ASCII data. In this case, it's just transmitting the boot log of the device. We'll talk about that later, of course. And the baud rate is how often this is happening, so how often it cycles between 0 and 1 for a message. And it would get confusing if you're going at twice the baud rate, the messages would end at the halfway point and the devices would get confused. If this was confusing, I apologize, but with anything in this presentation, if there's something I didn't cover well enough, please do search it up or find me online and ask me. I'd be more happy to explain in a more casual setting, but there's tons of tutorials, even not in the hardware hacking area, just for people working with electronics. A lot of people explain it really well in a lot more depth and cover it in more time. But I apologize if this was not clear enough. But let's say, hopefully it was clear, and we'll move on to how to use it. Now that you know what UART is, that doesn't really mean you know what to do with the hardware. So in this case, I have some pins that I soldered onto this router for the debug pins. I, in theory, don't know what they are. Just by looking at them, they're visually the same for the most part. Though the pins themselves are the same, but there are some clues we can look into. In this case, we're going to try and identify the 4 pins of a UART connection with no external tools except a multimeter. If you're not familiar, hopefully you are because you know some electronics basics, but the multimeter can measure voltage, amperage, and tell if 2 pins connect, or 2 points on a circuit board connect. That's what's going to be super useful for this one. These are some kind of random tips. When you see just pads on a circuit board like this, if it's square, it usually means that's the ground connection. Some manufacturers like to switch it sometimes, so it's worth double checking. But if you want to just eyeball it, if you see a square pad, it's probably ground, but always double check. And for continuity questions, like an RF shield, it will always be grounded. Basically, any exposed metal on a circuit board is going to be grounded, hopefully, whether that's like an antenna connector or the RF shield or like the outside of a barrel jack connector. You know that there's going to be a ground connection. It's the easiest one to find. So if you put your multimeter in continuity mode and put one lead or probe on the RF shield and just kind of go through all these pins, you'll find out which ones are ground. If you have a multimeter that beeps, it'll beep to tell you that that's a ground connection. VCC, which is the voltage pin, the trace is usually a little thicker over these connections in the circuit board itself because it actually has to carry power, and for physical reasons, you don't want the wire to be too thin. But in our cases, we kind of want to ignore that. It's also easy to use with a multimeter. So if you want to put your one lead on an RF shield or the ground pin once you identify it, and use the other one to measure these, UART, when the device is powered up and sending, as we mentioned, fluctuates voltages, while VCC will just stay stable at some voltage, like 3.3 volts, 5 volts, 12 volts for some reason. May happen, but it would stay like that. And let's say we have a 4-pin connector, like over here, and we found out this square pin is ground. let's say this pin over here is VCC and there's two left, and that's RX and TX, like we see in this diagram, you don't really need any fancy ways to figure out what they are. If you know the baud rate, you just plug them in at random, and you get garble info. To unplug them, switch them around backwards, and you probably got them right. Assuming you know the baud rate, of course. There are some tools and a script I will share that, not that I didn't make, a very famous one called baudrate.py that just goes through all the possible baud rates and you see which one is human readable text. If you just flip your RX to TX pins every time you check, you're bound to get across the right combination. Of course, this isn't the most optimal way, but this is for the cheapest possible way to figure out what the UART pins are responsible for. Another way of doing this is with logic analyzers. In this case, I'm using a Salier, very expensive 16-channel logic analyzer. You do not need one of these for this. If you can see here is a little drop-down menu. It says 500 ms/s. That's 500 mega samples a second. That's a lot of data sampling. It will fill up your RAM with data. You don't need this for identifying UART. I dropped it down to 20 mega samples a second. That's still a lot. A lot of cheaper logic analyzers, you can find some for like even $15, will not support 500 mega samples a second, but you also don't need it if you're just trying to find out which UART pin is which. But in this case, I have this tool available to me, and it makes pretty graphs, so I'm happy to use it. This is actually the same thing that I screenshotted earlier to show what the UART protocol looks like. If you see here, I have hooked up 5 connectors because there's a 5-pin breakout. I found out that the rightmost one, let's see, in this picture was ground. So I'm just looking at these 4 because I want to figure out what RX and TX are. And so by just hooking up 4 leads to the oscilloscope, I can see my channels here. So this is wire 1, 2, 3, and 4. I kind of knew this beforehand, but let's pretend that this information is not here, like showing which one's which. You can see channel 0, or the first connection, stays at 0 volts the entire time, and channels 1 and 3 stay at their positive voltage the entire time. And channel 2 is all over the place, and very nice square waves. So for starters, channel 2 is a great indicator of being the device's transmit pin, because it's obviously transmitting data, and it happens to decode to a human readable boot log, if you can see over here. Channels 1 and 3 are our best bet at the device's transmit pin, because it will stay high at the 0 as nothing is transmitting to it. The pin is just kind of by itself on the board. The logic analyzer will not transmit to it, it's only receiving. So if you're trying to find out which one the device's receive pin is, you could just switch between 1 and 3, and you'll find out which one's right by if you can interact with the device. But we can see here the boot log. In this case, it dumps you to the bootloader. If you see press any key to stop auto boot, then you can just quickly start hitting as many keys as possible. And with a lot of devices, if they run U-boot, for example, you'll be dropped into the U-boot shell, and you can do a lot of great stuff, but I won't get into that. One of the most common ones would be to dump the firmware over your serial connection, which can be really slow, because like the baud rate we mentioned, if the baud rate is one of the most common ones, which is 115/200, you're transmitting 115,200 bits per second, which is not a lot, at least for current times. So be wary of that. But again, as I've been saying a lot, we'll worry about that later. Another tool we can use for UART, funny enough, is the JTagulator. This is built for working with JTAG, which I will mention later in this presentation, but it also does support working with UART. In this case, it's the JTagulator has its pins broken out here, but they also have screw terminals here. And I just hooked it up to every pin here. I don't even worry about which one's ground or not. Just hook up all the connections, and you can put in a shared ground. Then you connect to it over your serial connection, which I will mention later in this presentation. And you get this nice shell with some nice ASCII art. In this case, we would set the voltage by measuring it, and then working with these UART options. I won't get into this because Joe Grand himself, who created the JTagulator, has some YouTube videos on how to use it, and they're wonderful. He does a great job of explaining what's going on, why the device is working, and what it's doing, and he explains it great. If you have a JTagulator or pick up a JTagulator, it's wonderful. But the basic premise is it will figure out which pins are which for you. UART is kind of a guess based off some ASCII returns, but JTAG it actually does more intelligently, and we'll get into that. And then the last step with UART is, now that we kind of know briefly what UART is, we've found the debug port on the device, and we have identified which pin is which. Now we can actually work with talking to the device. For using UART, you need to talk to the device with some sort of adapter. Your laptop or desktop probably doesn't have a serial port. If it does, all the power to you, but you can get these dedicated devices for cheap. I really recommend these UART cables. They come with 4 little wires: ground, VCC, RX, TX. I would recommend just getting the slightly more expensive one from Adafruit or someone like that. The cheap Chinese ones have some weird voltage regulation going on, and I've had a device not boot because the transmit pin was sending data when it booted and halted the boot process, and that took me like a day and a half to figure out. So just spend $3 more on top of your $3 and get like a nice one. The link here is what I recommend. A note with these, and actually every adapter in general with UART, there is that red VCC pin, as we saw in our diagram. If the device is powered, so however you would normally power, either over micro USB or with a barrel jack, do not hook up the VCC connection, because you're attempting to power it over both. It's very rare that you'll need that. I generally recommend powering the device as it's intended with its barrel jack or micro USB, and then just snip like the VCC connector off if you want. I have fried USB ports on my old laptop. I've fried devices that way. It's really stupid. If you do enough hardware hacking, you know not to do it, but it happens sometimes. But you just generally never want to do that. In the devices I'm working with, I actually removed the barrel jack connector, and I'm just using my variable power supply to power it. It just makes it a little easier for me than trying to find the right power supply or the right adapter all the time. But power it the way it's intended to, and skip the VCC pin or this red one. A lot of mine just have this red cable snipped off. Back on track, there's also an FTDI adapter. It has some more pins, some more options, different protocols. Sometimes you'll want all of them. Again, tons of good resources for that online. They're pretty cheap as well. Just try to get one with a genuine FTDI chip, or you may run into driver issues. Then there are the Bus Pirate and the Shikra, which are more multi-purpose hardware communication tools. They have support for like I2C and SPI. The Shikra, I believe, does some JTAG stuff. Yeah, they're great. But note, the Bus Pirate does not do JTAG. We'll talk about its kind of sister tool, the Bus Blaster, later. And of course, the JTagulator. It's quite a bit more expensive than all the other ones, even combined, but it is quite nice for JTAG work, and if you want UART to kind of figure itself out. But let's say you have the Jeep UART cable, and you've hooked up to the breakout on the device with the right pins. You're going to need some sort of software to talk to it. The device you'll usually see is /dev/TTY USB 0. You may see some other ones. It's device specific. Just look up whatever distro you're using, or just look up where to find the serial adapter. Most often it's going to be TTY USB 0, 1, 2, something like that. But the software you'll want, on Linux at least, is either Minicom or Screen, GTK term if you want a little more comfort features, something like that. In these screenshots, I'm using Screen. But you want to, as I mentioned here, either add yourself to the dialogue group or give yourself permissions to basically have your user own the TTY USB dev file. Or you can just run Screen with sudo if you want, but yeah, just know that you have to have permissions for it. And then if you're using Screen, you just do Screen, then the serial device and the baud rate, and that's talking to the device. And then if you power on the device with the baud rate, we're assuming 115200 is the right baud rate, and TTY USB is the right device, then we sometimes will get a boot log like this. And this is the same one that the logic analyzer picked up here. Just kind of a few ways of interfacing with it. This one is just with the serial cable. And I could here just start spamming some buttons and get to the U-boot shell, but in this case I'm just showing that there is some information. as the device is booting up, just kind of debug information or just to see what kind of state it's in. A lot of the times though, after it finishes booting and it spits out all of its boot info, it'll either drop you to the shell or to a login prompt. And if you either know the credentials, look them up online, crack them, or something like that, you can log in and most of the time get like a bash or an sh just shell. Let's move on to JTAG instead of UART. JTAG, well, while UART is kind of named off what it's done as like an asynchronous communication protocol, JTAG is actually just kind of who created it, which is the Joint Test Action Group. Don't worry about it. But the purpose of JTAG is kind of to bypass all the silly stuff and talk directly to the CPU. It comes in all sorts of shapes and sizes. The JTAG protocol supports having multiple devices chained together, as you can see here. But it is just a kind of a bare bones spec. Every manufacturer that implements JTAG will build up on it and add their own features and whatever the developers need for debugging. And it's kind of no JTAG between manufacturers is alike. They're highly specific to devices. There's a feature such as like the bypass command and things like that that the JTagulator uses to figure things out. And we'll get into that later in this presentation. But if you see kind of any pin breakouts in a row, like these 2 rows generally, ranging from 20 pins, 16 pins, 14, 10, or just 4, even sometimes a cluster of 4, it may be JTAG. In this case, the circuit board, whatever PCB this is really nice. It not only clearly labels what's what, but apparently even some headers came pre-soldered, which is great. This is a kind of more technical diagram of what JTAG is. JTAG is where you have data in, data out. TDI is data in, and TDO is data out. And you can see it's kind of chained between devices, between returning. So one of these pins is going to be TDI and TDO, which you're looking for. Also the clock signal and some other stuff, but we don't really need to get into this. Highly recommend watching some quick YouTube videos or reading a blog, as always. It may seem really boring at first, but if you spend some time gleaning some information, you will love it. At least I think it's super fascinating. But as we started working with UART, let's say now you found some sort of cluster of pins on your circuit board and your PCB and your device, and you want to start working at it. Again, you'll need some sort of adapter. There are scripts for like the Raspberry Pi where you can hook up some of its GPIO pins, general purpose input out, to kind of these pins, to the device to try and do what the JTagulator does. Same with an Arduino. I think there's something called the Blue Pill, which is the Blackmagic Probe software on an Arduino, if I remember correctly. There's things like that. But if you want, there is dedicated hardware for interacting with these things. They are a bit expensive because JTAG takes some more overhead on the hardware side for building an adapter for. But the JTagulator, Bus Blaster, Sheikra, and Blackmagic Probe are all great. Highly recommend. Blackmagic Probe is for working with ARM CPUs, and you can just get, it works as like a GDB adapter, virtual GDB adapter, and you can just go straight into it. But the Sheikra and Bus Blaster, as I mentioned earlier, are general purpose tools. The Bus Blaster is like the big brother of the Bus Pirate. It has some JTAG support, has some other nice features. It's a lot faster. The Sheikra is also another great general purpose tool, and the JTagulator is just wonderful for JTAG stuff. It does not interface with JTAG for you. Its whole purpose is just to figure out which of these series of pins is what, and then from there you'll need some sort of JTAG adapter. And yeah, JTAG is wonderful, and eJTAG for ARM devices, but you can have remote GDB. You could have basically a GDB running on the CPU itself on the target device, and you can step through everything it's doing. You can dump the flash if it's talking directly to the CPU. You've basically unlocked God mode on your device, and it's amazing. If you don't want to go the JTAG route, I want to mention the JTagulator because I didn't do a full walkthrough of this. I was kind of planning to do that for this talk, but again, Joe Grand, the person who created it, does obviously a much better job of explaining it. Just look him up on YouTube and find his tutorial on the JTagulator. All you do is you find what ground is, you hook up ground, you put up all the other channels, and you follow some simple instructions, and it goes through and it just works a lot of the time and finds your JTAG pin out. Then you put the corresponding pins on whatever your adapter is, and you are connected to JTAG. Again, it's highly manufacturer specific with JTAG, so no guarantees on what you'll see, but Google it, DuckDuckGo it, you'll find whatever you're looking for. If it's not device specific, you can look at what similar devices are doing, like if you're working on a IoT camera or like an IoT cooking device, and other IoT cooking devices have someone published a blog with showing what they did over JTAG. Just play around using things like URJTAG or OpenOCD, or if you're on an ARM device, Blackmagic Probe, to just bypass all of that. You'll see all the things that are available to you. A lot of times, if you just want to dump the flash and get out, that's totally fine. But moving on, let's say you don't want to interface with the debug pins. There aren't any debug pins or something like that. You can just interact with the hardware directly, because these storage chips or these flash chips, they contain all the secrets. In this case, I have a little digital microscope pointed at the storage or the flash chip here, like NAND flash, something like that. There's universal chip programmers. This is just an Amazon query for them. I really recommend the TL866, as I'll show later. But they come with a bunch of adapters that the chips kind of go into, and then you can pull all the information from it. And a lot of the time that's full device firmware, file systems, or great stuff like that. You will need to know what the chip type is, and if you can find this kind of essentially a serial number, kind of, it's not device specific, but it's like an identifier. If you just plug that into your search engine of choice, you'll usually be met with a ton of data sheets, hopefully. But it's very likely you will. From there, if that device type, like this is a TSOP 48 chip, you will put that into, if your chip programmer has a adapter for it, you can put it in, run some software, and dump all the contents from it. You can also write contents to it. But you do need to know the chip type and package type, so basically this information here, and you need to know the physical shape of it. But if you find the data sheet by looking up this, it'll tell you probably like TSOP 48, TSOP 32, if it's a 8-pin SPI clip or SPI chip, anything like that. If the manufacturer is annoying and decide to like grind off this information, I linked a cool tweet here where they use a highlighter and some UV light to kind of get that information back. My joke here with Mini Pro is the TL866, which I use for my chip dumping, has really only Windows support off a CD for its software, but someone made an open source tool called Mini Pro, so highly recommend checking that out. This is the process of me desoldering the flash chip here, which is you put some flux on it, melt it, put some low temp solder, take the chip off. If you have low temp solder, it's really helpful because it stays molten for a long time, but you can just take a pair of tweezers and lift it off. Then I clean up the pins to make them nice, clean up the solder on the chip itself, and then my TL866, which is this gray box here, has an adapter for this chip type where you just kind of push down, put the chip in, and read the data off it. And that'll spit out a bin file if you've done it correctly, and on this case, that's the fs.img that I dumped that I showed earlier in this presentation. And then kind of from there, the question is, what can you do now? Well, getting the device firmware is super useful. If it's not available online just from the manufacturer, you could pull it from the bootloader, like U-boot. You could sometimes, if it has the device has an SD card, you can put in an SD card, and in U-boot dump the memory, just specify from the start and end address to an image on the SD card, and boom, got it. You can do it over serial too, but it's a lot slower. JTAG, sometimes if you can communicate to the flash chip through the CPU, you can just tell it to dump all of its address space. And of course, you can do the hardware route, just take the storage off and tell it to give you all its secrets. Reverse that firmware, get all the secrets from there. If you want to make modifications, if there's CRC checking or some sort of hashing on the firmware stuff for validation, just look it up. If there's any keywords that are showing up like CRC failed, look it online. Basically, the device is trying to validate what it's being flashed. You can bypass sometimes if you are met with a bootloader like U-boot, you can actually sometimes just patch out the part of it that does the validation, which is super fun. A lot of the cheap IoT devices have undocumented backdoors, which is kind of sadly common at this point, where just open telnet ports with some credentials or kind of like port knocking, it'll open up a shell. It's so common. A lot of devices are also just not, it's not advantageous for the manufacturer to put security in it for price reasons or to have each device have a unique password. But even if they do, you can find a lot of undocumented features or take advantage of it. If the device has grep installed on it and you have a shell, just look around for like secret and tokens. Maybe you can get private keys or authentication tokens, anything looking like that. Look at the traffic. If you see it communicating to some sort of command server and sending a bunch of telemetry, like if it scans your network and sends a map of that information, it might be cool to intercept that and probably block that. But you can find out a lot of cool stuff like that. And you can also see if you are monitoring the traffic, you tell the device to do a firmware update, you can see what it's reaching out to. And if it's over like plain text HTTP, you can just kind of replace that with your own firmware. And if you want to, you can get a shell that way. Sorry, this presentation is kind of all over the place, but I hope some of the words stick. Overall, even if you don't know what you're doing in a lot of the cases, just knowing some words, phrases, and acronyms can get you to a shell. If you're more familiar with a lot of Linux stuff, you don't even need to worry about the hardware at that point. But overall, thank you so much. It's been a long time if you're still tuned in. I really appreciate that. These are some of the images I took and some free template I used. Thanks so much. Please feel free to find me online. I'll be in the Bug Crowd Discord on BusesCanFly basically everywhere. Twitter, Discord are great places to reach me. I'm happy to chat about hardware hacking whenever you want. Just let me know. And thanks so much, Bug Crowd, for this opportunity.
I'm just going to go ahead and ask the most common question that got asked. So a lot of the questions I saw both for this talk, but I feel like this is just a general hardware hacking talk, is like, how do I get started? And I feel like you kind of covered it in the talk, but, you know, compared to say web hacking, I feel like, you know, hardware hacking has got a little bit of a higher barrier to entry, right? Because you need to have actual physical tools that you wouldn't just have anyway, like maybe a computer for web hacking. And also you need to have devices to hack. So is there some kind of like platform or some kind of, you know, generic way to get started? Like, for example, for lock picking, there's this particular master lock that everyone kind of recommends to start with, and that's your first lock that you learn to pick, and then you kind of move on to these different locks, and people have kind of created this like almost pathway for learning for lock picking. Is there something similar with hardware hacking or not really?
Kind of both ways. I mean, so kind of like with any other part of like, how do I get into hacking? It's a broad scope. It's like it's a big question. There's a lot of devices a lot of people have been beating on for a long time. Like there's this old Linksys router, this like WRT something or WRG. It's this old blue thing. Like I mentioned in the talk, I pulled one of them out of electronics recycling, like basically a dumpster. And then with a $3 UART cable, that's enough to get like a shell and work with it. Like, but also cheap Chinese IP cams are usually great. If you find a blog where someone's like talked about doing some hardware hacking, or if you just look up like UART shell root, you'll find some devices people have worked on. I use the WiseCam V2 a lot. It's this $25 Wi-Fi connected camera for demonstrations because there's a bunch of ways to root it purely through software, just firmware. There's multiple ways to root it through hardware. It's great. But yeah, basically any device you find online where someone's rooted it with hardware, go for it. There's not a lot of cheap IoT devices that are very secure, especially on the hardware side of things.
Awesome. Okay, so basically look for blogs or write-ups or something that already exists and then try and buy that exact hardware. That's
yeah,
cool.
Totally.
And in terms of like cost, when you're starting out, like how much would you expect to pay for, I know you covered this, but maybe for a device and a UART cable or anything else that you might need to get started? Like, do you think it's like $10, $50, $100, talking like US dollars?
So depends on what you want to do. You can spend a few $1,000s on some crazy devices and tools, but you don't need that to get started. If you want to buy a $3 Arduino clone, a $3 cable, and then ask someone for an old IP camera they're not using, $6. If you want to buy a brand new device for hacking it, go for it. But I mean, a lot of people have these like old devices kicking around, like old routers from a non-technical person's house, or like old security cameras, modems. Just ask around. Someone definitely has some old hardware they're looking to get rid of that's just clutter for them.
Nice. All right, that's cool. That's cool. You're convincing me. So I know that holding up Jay, and Jay is a hardware hacking guy. I know he does a lot of car hacking stuff. So I know Jay's got a bunch of stuff he wants to ask. Jay, take it away.
All right, thanks, Luke. Hey, BusesCanFly. So I know that a lot of hardware hackers started with UART2 serial converters and also JTagulator and bus pirates. As a hardware hacker, what is your favorite tool that you love most, really?
Oh man, that's tough. I think it changes. Basically, whenever I get a new toy, that's my favorite one. But there's a lot of like really multi-purpose ones. Gosh, I don't know. I think I like some of my logic analyzers or an oscilloscope a lot. It's just really cool to visualize a lot of the hardware communication that's going on. But I like pretty graphs. That's about it.
Okay. And now, in terms of, because you're also interested with car hacking and automotive security, what do you focus usually when you try to be in a bug bash, or if your target is a car as a hardware hacker?
So it depends. Honestly, with a lot of the, like car hacking bug bashes I've done, I'm focusing kind of more on the Linux side. Usually you'll find, like I've worked with some cars where it's pretty hardened and then there's a serial connection side, a UART breakout, and it just drops you to root on the infotainment system. Normally with bug bashes, there's not enough time, or I'm not really allowed to just pop the plastic on the car and get into the hardware. But if you're working with CAN networks, like the OBD2 port on the car on the dash, there's a lot of good hardware tools for that already. If I was doing more of a long-term thing, I might order something or build up some sort of custom tool for this device. Like I know Ian Tabor, Mintinet, built some custom Arduino Bluetooth stuff. But for the most part, I use available cheap OBD2 dongles or just focus on the infotainment side of things.
All right. Yeah, pretty much the same with me as well. And I also use like OBD tools for testing cars. But yeah, thanks for sharing that one.
Thanks so much.
I have a pretty dumb question, but it's more a question that came from one of our people in Discord. It's a really good question, in my opinion. How do you actually take notes for something like hardware, considering it's a physical device? Do you like take pictures or something like that? How do you kind of go about a methodology for it?
So I'm pretty unorganized, but sometimes I just take a Sharpie and draw on the circuit board itself. Up to you if you want to do that, but like just drawing an arrow to a pin and labeling what it is works for me. But I mean, if it's hardware, you can draw a little diagram. If you're mapping out 16 pins, you can draw 16 rectangles and point an arrow to that. But with a lot of it's kind of trial and error. If you're like trying to figure out a UART interface, you just work pin by pin. But overall, same way you take notes, however you want. Maybe like a Trello board or something isn't as easy, but hand notes on a piece of paper would work.
Sweet.
Yeah, I also have another question. Oh, sorry, Sajib, do you have another question?
Oh no, that's okay. Go for it.
Okay, so I think this is my probably last question. So I think most hardware hackers or other hackers who have been to IoT security have bricked most of their firmwares and I mean their devices, and then I've seen in the question in Discord that they have like, maybe they're scared to play with it because they might break their router or they might break their device. So what are your what can you advise to them if somehow they break their device? Because I know that there are ways, but from your side, just want to know, how would you advise them?
Sure. I mean, this is pretty device specific, but there's a lot of things to look for. Sometimes, or usually, the manufacturer device will have firmware updates published on the site. A lot of hardware does do automatic updates, but they'll still upload firmware. And if you didn't corrupt like the bootloader, just the normal like Linux land stuff, then you can just flash the stock firmware and go from there. If you need a more low-level stuff, like I mentioned, JTAG, if the SPI flash chip is connected to the CPU, you can just like rewrite it all with the original firmware. Or if you're doing the hardware stuff that I mentioned, where you pull the chip off to read the data, those chip programmers also can just write data. So if you read your data, save it, brick it later, and then reflash it onto the chip, you should be good to go.
Right, thanks. Because I just want to clear it from the people who are asking it in Discord.
Yeah,
So thank you.
no problem. And I think if you're afraid of bricking things, start cheap, but don't be afraid. If you break something, it's always the best way to learn. I have bricked a car that an OEM has left us to use, and it was fixed. Go for it.
Yep. I've also bricked my other car as well, and went to the car manufacturer for it. But it's fun.
You learn fast when you break a car.
Well, thanks so much for coming, Buses. We really, really enjoyed it. It was a really good talk.
Thanks so much.
And yeah, it's been great having you on. So thanks, and hopefully we'll see you again in the future level ups.
Absolutely. Thanks so much, everyone.